Yes, sir.
Okay. Uh, to all, one and all present in this session, and thank you for the introduction. So, today I'm going to talk about this grid integrated solar energy conversion system using artificial intelligence. So, before that, let me share my screen. Is it visible?
Yes, sir, it is visible, but kindly make it into full screen, sir.
Okay. So, just 1 second. So, is it visible
Yes,
now?
sir. Yes, sir. Correct. Fine, sir.
Okay, thank you. So, yeah, so I am Dr. Animesh Kumar Sahu. So, I belong to the Power and Energy Research Group at IIT Dharwad Electrical Engineering Department. And currently, I think already brief about my research work has been given. So, I'll not delay much. I'll start the topic directly. So, my content for the today's talk will be mostly some introduction, then AI framework for grid connected photovoltaic systems, then application of AI for power system design, and application of AI for forecasting requirement in grids with photovoltaic systems, then application of AI for power electronics converter control, then application of AI for monitoring in a grid having solar photovoltaic systems and all its components. Then related to the above discussion, some future research trends and outlook. So let me go with introduction first. So as we know, over the last few decades, AI has emerged as one of the most prominent areas of research due to its capability to automate systems for enhanced efficiency and performance. So it enables systems to learn, reason, and make decisions much like humans by training them with a set of complex instructions. So if we see in perspective to power system, so the application of AI for digital transformation in power system has been identified to have massive potential in the air. In it helps in improving stability, reliability, dynamic response, and other essential advancement required for the power system network. So currently, if you see particularly AI techniques, how it is helpful, if you see the figure one, it can be used at different perspective and different field of applications in a grid connected PV systems. That may include your design, forecasting, control, designing the control, any optimization technique, then maintenance, of course, and any security, cyber security aspects of the power system. Nowadays, the important aspect is we have much more data availability in a PV power system operation that has advanced the development of AI, because as we know in artificial intelligence, we have to deal with several data, and nowadays it is well available, and using those data we can develop different state-of-the-art AI algorithms that can by which the system can learn in the process, and it will help in design, control, and maintenance aspect, and hence improve the efficiency and reduce the response time. And There are several research papers which have mentioned the application of artificial intelligence in solar PV system. But if you see them, the existing papers, their discussions or their analysis mostly focus on some narrow perspectives, like their field of applications, and based on that, they try to compare those algorithms and they try to comment on that. But if we talk about in a different perspective, the techniques they develop, and if we deviate from the field of application, those techniques may not give that much accurate information as required by the model or the system, you can say. And as you know, though there are so much data availability in the PV power system, so those are mostly, you can say, time series data, and that may suffer from noise and incomplete data set or anomalies in the data set. That's why we go for data pre-processing, and that is one of the most important tasks it is considered while we utilize the scope of artificial intelligence. If I go to the next slide, it's basically the framework, a framework for grid connected PV system. And as we discussed that AI for power system mainly classified into 5 classes, maybe optimization, data exploration, classification, regression, and clustering. And in recent years, there have been so many AI techniques for system design optimization for the PV grid connected PV system has been developed, and intelligent PV plants have been developed using different optimization, particularly linear programming based optimization, and those are being used for sizing the PV array, the PV panel array, and particularly along with the operation and the sizing of energy storage system. And also further, with increasing access to operating data of the power system, AI implementation has been a significant rise along with the improved accuracy. Okay, so particularly when we say theoretically a mission profile in a grid connected PV system that handles, for example, the data set corresponds to environmental factors like location in terms of like how much is the temperature distribution, the irradiance impact, humidity, etc. In addition to that, energy estimation, annual power generation, and other graphical interpretations. So these data sets actually important. Why? It helps in PV system designer in identifying the operating condition of the photovoltaic plant, and it will assist or it assists in extracting the minimum average and maximum power output from a grid connected PV system, that the PV system can inject the power to the grid. Now, if you see the application of AI for power system design, conventionally, we mostly rely on numerical simulation. Most of you have been doing this kind of offline simulations. So, based on some equivalent circuit model of the solar panels, and those are being used to discuss or describe the system operational performance. But what we see, these parameters we mostly use analytical approaches. But the problem with these analytical approaches is that several assumptions or approximations we take into consideration while we do this kind of numerical simulation, and that approximation, when we reflect into the accurate actual model, that may result in result in errors, modeling errors. So in that perspective, so this we can say numerical methods we can, in other hand, have proven to be a better solution. Those methods, as you know, can be Newton-Raphson, nonlinear, least square optimization, pattern search. Although these methods are computationally demanding, but parameter identification was also can be accomplished using methods like Markov chains, etc. So these methods require data that cover a large time span. Therefore, in that case, this kind of data are not available. This conventional method, that's why, cannot be implemented. So what methods, for instance, let's say we want to identify in a PV system what are the parameters of a PV system. So that can be used actually to accurately model the PV system in a grid connected application. So, for instance, these two types of model we use for designing a PV system. One is single diode model and double diode model. So, if we see the approach, the algorithms we use, let's say genetic algorithm, that can be used to achieve parameter identification with a double diode cell. So, what it does, it basically uses the diode voltage as a function of their temperature, and using that, it estimates the currents and shunt resistance in the double diode cell, solar cell. Further, if we use something kind of particle swarm optimization based parameter identification, that can be applicable to both single and double diode solar cells. And in this case, the fitness function basically is used as a root mean square error, RMSE, and that dependent on error function of single and double diode model as well as the solar panel. So using this optimization and algorithms, the results that we receive that identify the best individual from the final generation that closely trace the experimental IV curve with good convergence. So that's how we accurately able to model the particular solar cell or solar model, solar PV model, and that can be used further to integrate them into the grid side. So there are different types of parameter identification algorithms are available, which uses mostly comes under the artificial intelligence perspective. So as I told, one is genetic algorithm with artificial neural network. So if you see the advantage, mostly it applicable to both discrete and continuous, complex, and all other kind of data sets. And intermediate failures do not affect its end solution, whatever the parameter you get, and any kind of failure that doesn't affect the identified parameters. And the disadvantage with that, this is repeated fitness function evaluation affects the processing time of the approach, like the time required for parameter identification. It is impacted by the repeated fitness function evaluation, and if it is trapped in local optima, this approach will provide incorrect results. So if you see in comparison artificial neural network, so it is quite easy to implement with high precision factor and computational time also efficiency. Means it computational time is lesser as compared to if you use the genetic algorithm, and but it lacks a robustness on the other hand and consider only single objective or single distributed system generation at a time. At a time, only one type of distributed generation system can be considered under this. There are other algorithms like BAT algorithm that needs few input parameter, and it has a simple structure and robust performance, but it results in slow convergence speed. That means the parameter identification time is it requires more and more iterations to get into a converging solution, and it is has low optimization precision. Then if we see generalized regression neural network that easily maps the complex relation between independent and dependent variable, and efficiently handle the noise in the dataset, because as I discussed in the previous slides, there will be definitely noise when you deal with an anomalies. Also, you deal with a large number of data sets which are currently available. So in that case, we require this in this, let's say, generalized regression neural network that can handle the noise in the data set, and it has high processing time as one of the disadvantages, because it contains large structure of neural networks. And one of the important method is particle swarm optimization. This also requires a few parameter per adjustment, and it is robust enough to handle parallel computation, but it doesn't suitable for scattered parameter, and it's difficult to identify the initial design parameter. And lastly, you have this adaptive neuro fuzzy inference systems. So this also helps in finding the global optimum and capable of handling complex optimization problems that you design to identify the parameters. But again, as complexity is involved, so it also relatively complex implementation is an issue. and maybe it also includes sometimes larger processing time. Now, if we see the application of AI for forecasting, why forecasting is required, because the reason for increase in solar PV has been seen over the last few years, and having accurate forecast for the power production fed into the grid has become more and more important issue. So why that has been seen? The reason for increase is primarily because of the reduction in investment cost, which is, you can say, if I take an example from 2019 to 21, there is a 10 to 20% decrement, but also factors such as incentives, regulations on technical requirement for building works and other directives also have played a role. So that allows the increased penetration of solar PV systems. And India is currently also targeting to install 500 gigawatt of solar PV by 2030. And as this increase is expected to continue, as we discussed in the future years also, so this grid connected PV system will lead to a higher changes in the electricity grid, because as you know, solar power generations are more random rather than it is uniform. So it will definitely change the modern power system, to the paradigm, you can say, and power generation profile also. There will be so much instability due to sudden changes in the weather, because it is also weather dependent. For instance, it depends on temperature, irradiance, humidity, etc. So again, the liberalization of the electricity market also nowadays has led to the introduction of spot markets for electricity, which played an important role in balancing the supply and demand. So generators, retailers, large and customers and communities have to estimate their output and demand accurately. So that's why this forecasting method, as it is dependent on weather, so it is a process of chaotic system, and that motivated the development of intelligent techniques that are dependent on statistical and stochastic models, and they enable long-term planning by providing a broad understanding on how distribution systems and loads behave. So it will help in balancing the electricity production and consumption, and will establish the markets for energy and control reserves. However, the increase in PV made it difficult for the market players to manage their systems, because they typically have difficulties to forecast solar irradiance and PV outputs. So, if we see what are the different methods that can be used under the artificial intelligence scope, and how it is used in a proper PV system, solar grid connected PV system, you can see the figure number 3. So there are different points where we require different kind of data to feed, and also we have to develop different models based on the artificial intelligence under artificial intelligence scope. So those are what are the forecast models that involves algorithms. If you see this left side table, the algorithm can be LSTM, neural network technique, wavelet decomposition, then artificial neural network, or Gaussian process regression. So every algorithm, you can see, meets different kind of objectives. So you can say those are kind of intelligent methods, and they help you to predict the solar irradiance. They can forecast the solar irradiance maybe day ahead or month ahead. And let's say, for example, LSTM neural network technique, it will develop its main objective is to develop a multi-time scale model, and it can handle the nonlinear data and memorizes long temporal relationship in the data. But the disadvantage, as you can see, it takes longer training times and easy to overfit, and also sensitive to random weight initializations. And in comparison, wavelet decomposition, if you see, this decomposes the raw solar irradiance data into subsequence. It efficiently models the non-stationary environmental parameters without losing information. Also, it effectively handles the short time scale solar irradiance, But it again, as it is decomposes data into subsequence. So what are the choice of decomposition level? That is also play important role. And then redundant representation of data also is one of the disadvantages. Then if you see artificial neural network, so it can accurately forecast under strong irregularities and rapidly changing scenario in the atmosphere. Modeling abilities with the different elements of the input data to form a relation in the network structure is advantage, and is also sensitive to dimensionality of the data. It identifying preliminary settings and functions according to input data. Then the fourth one, you can see the Gaussian process regression. It helps in developing probabilistic renewable energy management system. It directly captures the uncertainty in the data. Then probabilistic prediction for computing empirical confidence intervals, but it again requires you can see the large data set for prediction, and it is also less efficient in high dimension spaces. So previous table is basically the solar irradiance forecasting techniques. What are the intelligent methods we can use? Now we'll compare what are the intelligent techniques for output power forecasting, solar output power forecasting. There are different methods again we can use. It again comes this left and artificial neural network, fuzzy logic, artificial neural network only, and then back propagation neural network also. So if you see the wavelet and ANN technique, so it doesn't require multi-channel signals. It automatic and online forecasting can be achieved using this technique. But it's again time consuming and removing a large amount of useful information from the original data. Then the fuzzy logic is basically, as you know, is an intuitive design and quick response. It demonstrates the flexibility in forecasting action. It doesn't demand the exact model of the system. The model information is not that much important in forecasting the output power, but it cannot predict varying process with the time delays, and multiple tuning parameters affect sometimes the stability of the approach. If we see the artificial neural network, there are intuitive also and quick response like fuzzy logic. And the forecasting action is demonstrated just by the definition of weights along the layers. And the adjustment of abundant parameters affect the stability of the approach. Choice of network size and structure affects the prediction accuracy. And shape of accepted input function needs to be checked for accurate results. And finally, the back propagation neural network, if you see, so no additional parameter tuning is required. Continuous learning to identify the relevancy and difference in the input data. No prior knowledge is required for learning, makes the approach flexible, and its performance only depends on the types of input data, and is sensitive to outliers and noise also in the data is present. Now, if we see the control, now everything we discussed till now, till the PV system, if you see the figure 4, till the PV panels generates the DC power, and then you have basically a DC-DC boost converter if you want to connect the PV system into the grid. So you'll have a DC link voltage, and the PV panel, if you don't generate that much DC voltage, you require a DC power interface, DC-DC boost converter you may use. And so those, when power electronics comes into picture for grid integration or some kind of other application of solar PV system, as we know, these power electronic converters mostly controlled by some kind of designing a firmware controller, software-based controller. And in that prospect, also we can have a scope for involving the artificial intelligence-based smart control techniques that can mitigate the usual issues followed by the conventional control methods. So if you see in the figure, if you see there is a PCC point of common coupling where the inverter has a breaker, and that breaker, when it is on, that connects the inverter to the grid. If the breaker is at one position, the inverter, the PV system runs in islanded mode and it supplies the local load, you can say ZL. But when the breaker is at point 2, so it is operated in grid connected mode. So we can see there are two modes of operation that a grid connected PV system can implement. So the conventional controllers for the inverter is basically, we can see it is maybe a grid following or grid forming type structures, and mostly the controllers in DC-DC or the DC-AC type, they use mostly this linear type controller because that is easy to implement and mostly approved by the industry expert industry users also, and they are mostly linear type of controller. But if we use this AI-based controller, the accuracy of the controller it will increase, and also response time will be highly improved. But the problem will be the transient error, and it can to transient error it can improve significantly. So what if you see the diagram, the AI technique part, if you can see, it takes the data mostly the grid part, like the voltage measured at the PCC, frequency at the PCC, then current measured at the PCC. So using those data, you have to develop some function, and that function will you have to train with that, and from that you have to develop your inverter controller. So, for instance, let's say there are different you can say objectives a inverter has to meet when it needs to be grid connected. Some of the important thing I have shortlisted here. Let's say for one is this anti-islanding protection and low voltage right through. So those are some of the important grid code requirement when the grid connected PV system need to be connected to the grid. So in that case, those basically in commercial inverters, if you see nowadays they mostly use the classical linear controller. But what we can be also done that instead of this classical PR based controller for this grid code requirement, we can also use kind of fuzzy based inverter control, and it can be used actually to tune this PID controller, and instead of going with theoretical based or frequency response analysis based tuning of PI controller, we can use some kind of, let's say, fuzzy or unfused based inverter controller that can, based on the real time grid operation, it can automatically update this gain tuning of this controller, and that's how the inverter can respond to different grid events smartly, and instead of going with a classical way of control. So if you see you can see there is a comparison. One is a low voltage right through. So to enhance the low voltage right through capability of the inverter, we can use these AI based techniques such as, let's say, fuzzy logic control. So if you see the figure 5, in normal operating condition, we require some kind of current reference to be injected to the grid, but when the fault happens or some kind of you can say low voltage fault happens, according to the new grid code, it is mandatory that the inverter should stay for some time, and then if still the fault is not clear, it has to be tripped. But during that stay, inverters should not trip. So that is how we have to develop the controller, and if the with the proposed or the design controller inverter can sustain that fault for certain time, we can tell it has successfully ride through the low voltage fault. So there are two kinds of operation. One is, let's say, during normal operation, we can go with the top and normal control, which basically, if we consider as grid following inverter, this is basically uses a phase lock loop based current control technique that generates the reference current for the inverter to operate during normal operating condition. But let's say during fault happening, so instead of using that conventional method, we can include some kind of intelligent control technique that can quickly help the inverter to stay connected for certain time or right through the fault, and instead of without getting tripped. So different techniques, for instance, fuzzy logic control we can use. Then we can use particle storm optimization also can be implemented. It will help to improve the low voltage output capability for the total nonlinear system, where fuzzy logic control can be utilized as a vector current control plot for the ceiling voltage and perform low voltage output safety. Then one of the most important technique or operation required for the grid connected PV system. In the previous figure, I told you the islanding and grid connected operation. So in that, sometimes when the fault is clear, you have to again switch back to the grid connected operation from the islanding mode. Or if something happens, you need to be disconnected from the grid and make it or operate in the islanded operation. So that kind of transition we basically require for the grid connected operation. So in that case, so what we can do, so we can instead of using some data driven model or some kind of AI based transition technique, the switching mode can be more and more seamless, and it can there will be no kind of you can say during switching there will be no transient that will be faced by the inverter from islanded and grid connected operations. So if we see the particularly two techniques, this particle swarm optimization or fuzzy logic control, if we see their computational burden are comparatively low, and their reactive current injection during a fault mostly sufficient. But the problem is, though it gives advantage like fast response and simple and flexible no overlapping, it results in oscillations and overshoot, and also because this oscillatory response also is not recommended, because if your controller provides the oscillatory response, then whatever the current injection to the grid also there will be an impact on the power quality aspects of the grid current. So that is also have a certain kind of standard with the inverter needs to follow. Instead of sending bad quality of current, it has to be properly maintaining the power quality standard. So those are the some kind of you know disadvantage with this kind of AI technique, but it's of course gives a more seamless operation. Apart from the classical methods, as you know, we can use some kind of dynamic voltage distorter, because that time fault time you require some reactive power injection thing. But again, it is depends on voltage dependent reactive power control, and it sometimes leads to instability. And also, we can use static synchronous compensator, which also gives efficient control over reactive power control and a drop in voltage negative sequence. But its disadvantage is its low capacity in supplying active power, and it coupling transformers introduce many switches also in static synchronous compensator. And in both these methods, the computational burdens are high in kind of implementations. Now, other thing is the application of AI for monitoring. So this is a complete picture from the PV panel towards grid and all the components that can that require some kind of monitoring for a successful operation. You can see for the grid connected operations. If you start from the left side, if you consider the PV panel, so basically, these grid-connected PV systems operate in a rigorous and complex working condition. So definitely, for this, they may suffer from various fault events, and that fault can be at the component level, at the system level, or can be both. And that's why the safety and reliability of grid-connected PV systems are of, you can say, of utmost importance to ensure the efficient operation of the system. And for instance, let's say maintenance activities, including preventive maintenance, incorporating condition monitoring, fault diagnosis, and predicting the remaining useful life also require some kind of, some kind of AI-based techniques can be used to predict those parameters and just result in less frequent disconnection of the PV systems. Then if you see from the PV panel level, So there can be PV panel fault. You can see it can be delamination, cell crack, shorting of diodes, and there are glass crack can happen. And also because as we know, to run the PV in grid following mode, we require some kind of coordinated operation of battery energy storage also. So if you consider a solar PV along with the battery system, the battery fault also can be considered as a critical parameters to be monitored, like low temperature, high voltage storage, high rate cycle, water immersion, collision, inconsistent cell. So this is something from the DC, you can say the distributed energy sources or renewable energy sources side fault. And if you see, there are also combination box fault. If there is a combination between with different solar PV panel, so in that combination box, there can be oxidation or corrosion. Those kind of faults may happen. That may lead to kind of short circuit or maybe other related issues. Then, if you see, go to the power converters that basically required as a interfacing element or interfacing component for grid connected or PV systems. Those power converter fault can be particularly the component level, the bond wire melting, bond wire lift off, crack in bond wire, aluminum corrosion, delamination of die, etc. So those can be considered under power converter component based fault. Then again, as we know, we use some kind of filters on the grid side to attenuate all the high switching frequencies from the inverter output. And those filters may undergo thermal overstress, crack in dielectric, leakage in electrolytic, then bad soldering joints. So those things also need to be monitored. And then again, we relay our breaker, as you see, which requires to be operated for the similar transition. So that may undergo fault like iron core failure, coil failure, residue voltage, excessive current, high contact resistance. Apart from that, if you see from the system perspective, we can consider the generation side, distribution side, transmission side. So generator side, what are the system fault happens, then it can be capability of ramping rate that needs to be monitored. Optimum dispatch energy spinning is a requirement. And from the transmission side, what are the power flow fluctuations, those oscillations, voltage profile problems, stability problems, and the distribution perspective, like power flow fluctuation again and the feeder power loss, harmonic distortions, improper voltage profile or unbalance, loading of filters, feeders, etc. And this is all about the controller. If we come to the communication part, so if you see, there will be different kind of monitoring, remote monitoring system. So the communication fault can be sensor malfunctioning, disconnected of communication line, because there are different, when you start to use some kind of communication channels or communication network, so there will be definitely the risk of cyber attacks. So due to any kind of cyber attack or something, some communication line is disconnected or something, so that will result in again the fluctuation of power or maybe improper power injection to the grid. So those things also need to be properly monitored. And yeah, so this is all about the what are the, we can say, probable or faults or critical risk a grid connected PV system can experience from the different perspective. It is a picture has been given. Now if let's say this kind of fault happens, how AI can be used to monitor all kind of these things. So there are two things. One is, if you the left side is basically different types of fault, already I told you. So if I, let's say, now we'll go to the detection technique, because the cause and all is already there. So if I say the PV panel fault, we discuss what are the different type of faults. The cause can be physically damaged, then overheating, overexposed to direct sunlight, moisture in atmosphere, physical damage. So all these faults can impact result in reduction of solar panel output power, and that's how it increase the burden on DC-DC converter. So what are the detection technique that can be used? Either you can use visual inspection or thermography based detection, image processing based fault identification, or some kind of signal processing you can include in the controller that can continuously monitor those defects. Then what are the combination faults will result, because it will result in reducing power flow. Let's say one of the panel is disconnected, so that panel will not generate the required amount of current. So it will result in total reduction in power flow from the net PV panel. So that can use some kind of visual inspection or signal based monitoring again. Then when you come to power converter fault, so that can also may happen due to overheating of thermal joints, stress on the bond wire, environmental effect also can happen, thermal stress and overheating of power electronic switch due to any kind of fault or grid side fault. So what will happen? It will cause stress on the inverter operation and wear out inverter components, and it will reduce the operating lifetime of the inverter. Then what are the detection technique? So temperature sensitive electric parameters, we can see, we can kind of build some relation between the electrical parameters and their temperature relations. So any kind of temperature related things will happen, temperature will increase, those electrical parameters we see a abnormal behavior. From those behavior signatures we can detect those what kind of faults, and we can classify them. Then operating characteristics based monitoring using signal and learning approaches. Also thermal modeling and physics based modeling also will help in the power converter fault detection technique. And when it comes to the filter, grid side filter technique, so we can monitor the output voltage signal and also thermal image based learning approaches. And the relay or breaker based fault, we can use signal processing and machine learning approaches through measurement of contact resistance, coil resistance, and operating voltage. And if we see the battery voltage, then it will have impact like loss of active anode and cathode material, capacity fade, then thermal runaway, longer charging time. All this impact we may feel, and then detection technique can be data driven model again to find out or to estimate the state of the health, state of the charge, then thermal inspection, incremental capacity analysis, uh, then again remaining useful life prediction, all these things. Then if you see the lifetime estimation algorithms using AI-based technique, the conventional and what are the methods are available, we can use them. One is the reliability block diagram, fault tree analysis, Monte Carlo, and Markov analysis. So these are can be used to estimate the lifetime of a particular component in this grid connected PV system. So if we see the reliability block diagram, what are those applications? So it basically analyze the component fault by representing them in a block. It has simpler implementation, but drawback is external cases of human interference and priority-based events, so is not considered. And fault tree analysis basically identification of probability of each fault. It may be fault on the DC-DC part or DC-AC part. So it advantages external factors is accounted for and also assisted in designing. Interdependency is not analyzed in this fault tree analysis, parameter interdependency. Then Monte Carlo, if you see, generate a random events in computer model to count the instance of occurring the specific condition. It has high precision and less work in calculation and rapid convergence also. But canonical problems also has been identified, and estimation of functional exception of a lifetime model for repairable and non-repairable components. Then if you see Markov analysis, it mostly used for identification of transition rest based on failure and repair rate. It is easy to implement for a system where repair is possible. And but drawback is modeling is large due to state-based modeling with a constant repair and failure rate. So based on this, the future trends or outlook, if I want to conclude, This application of AI technique with different functions of the connected PV system has been identified that the process of digitization has a universal acceptance, and further this led to the development of various new approaches which you can say increase the integration of modern energy system with the grid. And mostly two aspects nowadays people are working on. One is the digital twin. So if you see the major shift in resistance, because digital twin has effortlessly increased the connectivity between physical environment, the data and virtual machines. And from the perspective of grid connected PV system, where it can be used with different modeling methodology that integrate energy forecasting, demand side management, control monitoring, and data visualization. So then cyber security, if you see, and as I told, when you have a total interconnected systems where power electronics dominated grid, the grid-tied converters are remotely controlled by a power plant controller and a SCADA-based system by a PLC, optical fiber, wireless communication such as ZigBee, cellular or LTE. So as this kind of extensive communication networks have been used, so they are definitely vulnerable to cyber attacks at the same time. And some of the important attacks are data integrity attack and denial of service. And this development of new standards for distributed energy system, resource cyber security, will definitely play a big impact on PV system. And yeah, so that's what about my short presentation on this. Thank you. Hello. Hello.
Hello, sir.
Yeah, so it's all about my presentation. Thank you.
Thank you, sir. Thank you for your thoughtful session, sir. We are grateful that you shared your expertise and enthusiastically engaged our participants. Before the feedback and questionnaire, I request you all to switch on the video.
So, hello. Hello.
Yes, sir. Tell me, sir. Animesh, sir.
So, what
Yes,
I
sir.
need to do?
Please switch on the video, sir. We will take a photo.
Okay.
Switch on the video, sir.
Sure, sure.
Thank you, participants. Now, you can go with the questionnaires.
Sir, may I ask you one question, sir?
Yes, please.
I want to ask you questions in a converter regarding converter, application in converters. Suppose we develop one algorithm. Then
Okay.
that develop algorithm we have to dump in MATLAB or what, and how it will be implemented in real time using DSpace or DSP something.
Yeah, so thank you for your question. So, two things. Are you talking about the classical control or something related to AI based control?
AI based control.
Yeah, so for AI based control, I mean, maybe you can design some kind of toolbox or something, but the thing is, first you have to, if you want to use in actual model, so before that you have to test it offline simulation, as you told, maybe MATLAB, Plex, or any kind of software. So in that you have to first design a model and you have to train your model, and then based on the training of data set, you have to ensure that whatever the model and it's you developed using AI technique, those are properly fine-tuned. And once you have developed that model, then you can generate its code and you can dump into the maybe firmware, whichever controller platform you are using, DSpace or Opalati or wherever, you can put there and you can run them in parallel in coordination with the physical inverter system.
Yes, yes, sir. And then we can compare with classical and AI and
Sure. But yeah, so mostly if you see in literature or some kind of research work, or if you see the industry approved inverters, companies like ABB, Toshiba, or some kind of you can say Impedix kind of or Danfoss drives type inverters, SMA inverters, they're mostly still running on classical inverter control. So using of AI in actual inverter system is yet it is limited to the research academy, or you can say the academic research point of view. Still, it has to go through the industrial aspects.
yes, yes.
Thank you.
Any more questions, please?
Sir,
Sir, good evening, sir. Hello?
again, one question, sir. Is it required to learn languages like a Python and all that?
I mean, if you ask me, being a, do you belong to electrical engineering or any other department?
Electrical, pure electrical.
And power and energy system, right?
Yes.
So, in my opinion, so learning Python and application into power system people is not that difficult, because in Python or something we are just using different API, you can say, from their library to implement certain things in power system. So we are not computer science engineer, we are not developing different softwares or something.